Hello and welcome. In this video, we are going to analyze a vapor compression refrigeration system. I have already transcribed the schematic into the TS diagram. So 1 to 2 is our isentropic compressor. 2 to 3 is the condenser. We'll call the pressure in the condenser side PC. And then from 3 to 4, we have an isenthalpic expansion process. Enthalpy remains constant here. And from 4 to 1, we have the evaporator. This is the evaporator pressure, PE. The evaporator pressure is supplied. The condenser pressure is supplied. Fluid is R134A. Mass flow rate is known. And we are asked to find the tonnage of the system, which means what is Q dot in the specific unit of a ton of refrigeration system. We know Q dot in should be in kilowatt, and it's just a conversion from kilowatt to tonnage. A ton is about 3.51 kilowatt or something like that. We are also asked to find the compressor power, W dot C, which could be in kilowatt. Okay, so let's start the problem. We'll take the compressor and the evaporator pressure as parameters so that we can add a parametric study after we solve the problem. So I've already launched the app, but let me go back to show you where the app resides. Obviously, it's a OpenSteady system, so we go through OpenSteady specific branch, vapor compression refrigeration, and the PC model should launch the app. The fluid is R134A. We go to the IO panel, and let's declare the condenser pressure. PC equals 1 MPa is 1000 kPa. Remember, it has to be in SI units. And pressure of evaporator, we'll call that PE, is 0.15 MPa, which is 150 kPa. Okay, so these are our two parameters, and their calculate registers their values. So now state 1 is the evaporator exit state, or the the compressor inlet state. So P1 must be equals P of evaporator. The mass flow rate is given to us 0.04. What else is supplied? At state 1, X must be equals to 1, because at the evaporator exit, for an ideal cycle, the vapor must be saturated vapor. So that is our state 1. At the compressor exit, the pressure must be raised to the condenser pressure isentropically, therefore S2 equals S1, and mass flow rate must be constant throughout the systems, m dot 1. That completes the state. Now to calculate state 3, we could go and start from scratch, or we could spawn state 2, duplicate it, copy it to make state 3, because some of these things are common. M dot 3 is M dot 1, P3 equals PC, and we know X must be equals, in the case, entropy is not the same, but quality must be 0 at the exit of the condenser. State 3 is our condenser exit. And finally, state 4 is after the expansion valve. What happens in state 4 is that the pressure must be equals P evaporator. Pressure drops to evaporator pressure in an isenthalpic way. H4 equals H3. And of course, M dots are equal, M dot 1. And that completes the calculation of state 4. If we go to the graphics panel, we should see something similar. The TS diagram 1, 2, 3, 4. Entropy actually slightly increases. It's not clear in the diagram that we plotted here. I exaggerated that. 4 is way to the right, but as you can see, even in the correct diagram, if you see closely, 4 is slightly to the right of 3. Okay, now that we calculated all the states and they look reasonable, let's go to the device panel. And device 1 is our compressor, operates between 1 and 2. And in a compressor, it's adiabatic. So that calculates the compressor power, negative 1.58 kilowatt. 2 to 3 is our condenser. In the condenser, heat is lost to the atmosphere. In 3 to 4, we have an expansion valve. There is no work, and Q dot must turn out to be close to 0, exactly 0. Okay, so that means we are on the right track. And finally, here is the cooling load. From 4 to 1 is our evaporator. This will determine the tonnage of the system. 4 to 1, there is no work transfer. So 5.28 kilowatt is our cooling load. If we convert it to ton of refrigeration, so this is our answer. So we found what is Q dot 4. And of course, we could go to the cycle panel, and because the cycle is complete, we could pick our answers up here too. For instance, you can find Q dot in is our desired answer in kilowatt, but you can switch it to tonnage. W dot in is the work that has gone in. This is the compressor work. And all the other quantities you can find. What is the maximum temperature in the cycle, minimum temperature in the cycle, etc. Or more importantly, what is the COP? But notice that the COP, COP is about 3.33 is given here for this particular cycle. So what will happen, suppose, if we increase the condenser temperature? You know from the Carnot analysis that COP should go down if the difference between the cold and hot temperature increases. So if we raise the condenser temperature, condenser pressure, then this temperature will increase, the temperature at which condensation occurs. So therefore, difference between TC and TH is being increased. If you recall, the Carnot efficiency is something like, Carnot COP is something like, for a refrigeration system, is TC divided by TH minus TC. I know it's not a Carnot system, but if you somehow increase the difference between TH and TC, you expect the COP to go down. So let's just check that. Right now the COP is 3.33. What will happen if I raise the condenser pressure? Okay, to do so, I'm going to go and just arbitrarily raise the condenser pressure. Let's say instead of 1000, we say it's 1500. Recall that the condenser, COP was how much? 3.33. Let's do a super calculate and check. From 3.33 it goes down to 2.22. So as we predicted, the COP has come down. Likewise, you can do any number of what-if studies using this what app. If you put the suitable parameters in the I/O panel, that's it. Then you can very easily change the variable and see its effect on overall quantities.